Hello and welcome to Eclectic Classes. In this video we will learn about various flow meters used in industrial applications. So let's move forward. Let's start with, what is a flow meter? A flow meter is a specialized instrument designed to measure the rate at which a fluid, liquid or gas flows through a specific point in a pipeline or system. Think of it as a wizard's tool for tracking the journey of liquids and gases. In the realm of technology and fluids, a flow meter combines technical prowess with a touch of magic, providing accurate and real-time data on fluid flow. It acts as a crucial guide, enabling precise control and monitoring in various industries. Why are flow meters essential? Optimizing industrial processes. Example: picture a master chef. Much like a master chef perfecting a recipe, flow meters optimize industrial processes. They ensure the right amount of fluid is delivered at the exact rate needed, enhancing efficiency across various industrial operations. Effective resource management. Example: imagine a garden nurturer. Acting as guardians for sectors like water treatment and energy, flow meters manage resources like skilled gardeners. They monitor and control the flow of liquids or gases, contributing to effective resource management. Mastery and quality control. Example: envision a precision robot. Flow meters play the role of precision robots on an assembly line, serving as quality control experts. Industries depend on them to maintain consistent product quality, especially in manufacturing processes that demand precise fluid quantities. In simpler terms, a flow meter is your friendly helper, ensuring the seamless flow of fluids, whether it's water in a garden hose or essential fluids in complex industrial processes. Visualize a flow meter as a wise guide overseeing the intricate journey of fluids, combining technical prowess with a touch of magic, like a watchful friend overseeing a pipe. Venturi tubes. Operating principle. Venturi tubes work like a nozzle to measure fluid flow. Imagine a garden hose with a narrow section in the middle. As water passes through this narrowed part, the throat, it speeds up, creating a low pressure zone. This pressure difference is directly linked to the flow rate. The faster the flow, the greater the pressure drop. Advantages: offers precise measurement of fluid flow rates, minimizes pressure loss in the system. Applications: widely used in water treatment plants for accurate flow measurement. Applied in various industrial processes where precise flow control is crucial. Limitations: can be costlier to manufacture and install. Best suited for medium to large pipe diameters. Orifice plates. Operating principle. Orifice plates act as flow restrictors by introducing a precisely measured obstruction in the fluid pathway. When the fluid flows through the orifice, it accelerates, creating a pressure drop. The degree of pressure drop corresponds directly to the flow rate, allowing for a straightforward measurement. Advantages: simple and cost-effective design. Versatile use in a wide range of applications. Applications: commonly deployed in HVAC systems for efficient fluid control. Ideal for industrial processes where a budget-friendly flow measurement solution is essential. Limitations: may exhibit lower accuracy compared to some advanced flow meters. Can result in a higher pressure loss. Other differential producers. Operating principle. Similar to Venturi tubes and orifice plates, other differential prod. Users utilize constrictions to measure fluid flow. The pressure difference created by the constriction serves as an indicator of the flow rate. Advantages: exhibits versatility for application in various industries. Features a relatively straightforward design. Applications: commonly found in chemical processing plants for flow measurement. Suitable for monitoring flow in pipelines. Limitations: accuracy may be influenced by fluid properties. Installation requirements can be critical for optimal performance. Laminar flow meters. Operating principle. Laminar flow meters work with the concept of layers. Imagine fluid flowing through a tube in perfectly parallel layers, like neatly stacked sheets of paper. The rate at which these layers move correlates with the flow rate. By measuring the pressure drop across the laminar flow, we can precisely determine the flow rate. Advantages: simple design based on fluid layering. Ideal for measuring low flow rates accurately. Applications: Widely used in medical devices for respiratory applications. Applied in laboratory experiments where precision at low flow rates is crucial. Limitations. Limited to low flow applications. Susceptible to disturbances in flow profiles. Variable area flowmeters. Operating principle. Variable area flowmeters, often known as rotometers, operate on the simple yet effective principle of changing flow area. As the fluid passes through a conical tube, a float or piston moves, adjusting the area through which the fluid flows. The position of the float provides a visual indication of the flow rate. Advantages. Simple and easy to understand design. Direct visual representation of the flow rate. Applications. Commonly used for gas and liquid flow measurements in laboratories. Ideal for industrial processes where visual flow rate monitoring is valuable. Limitations. Limited accuracy for precise measurements. Not suitable for high-pressure applications. Turbine flowmeters. Operating principle. Turbine flowmeters work on the simple idea of spinning blades in the path of the fluid. As the fluid flows, it causes the turbine blades to rotate. The speed of rotation directly corresponds to the flow rate, making it easy to measure the amount of fluid passing through. Advantages. High accuracy, especially for clean and steady flows. Well suited for measuring high flow rates. Applications. Widely used in industrial processes with clean fluid streams. Applied in measuring liquid fuel in automotive and aerospace industries. Limitations. Susceptible to damage from particulate matter. Not ideal for low flow or fluctuating flow applications. Vortex flowmeters. Operating principle. Vortex flowmeters capitalize on the creation of vortices, or swirling patterns, in the fluid stream. A bluff body in the flow causes these vortices, and their frequency is directly proportional to the flow rate. It's like counting the whirlpools in a river to gauge its speed. Advantages. Suitable for a wide range of fluid types. Minimizes pressure drop in the system. Applications. Commonly used for steam flow measurement in power plants. Ideal for chemical processing involving diverse fluid types. Limitations. Accuracy can be influenced by fluid properties. Not the best choice for low-flow applications. Magnetic flowmeters. Operating principle. Magnetic flowmeters leverage the principles of electromagnetic induction. By applying a magnetic field to the fluid and measuring the induced voltage, the flow rate can be precisely determined. It's akin to measuring the speed of a car passing through a magnetic field. Advantages. Ideal for conductive fluids. Minimal pressure drop in the system. Applications. Commonly used in water and wastewater treatment. Suitable for chemical processing with corrosive fluids. Limitations. Limited to conductive fluids. Pipe material can impact accuracy. Ultrasonic flowmeters. Operating principle. Ultrasonic flowmeters use sound waves to measure the velocity of a fluid. By sending ultrasonic pulses upstream and downstream, the time it takes for the waves to travel provides information about the flow rate. It's akin to timing how quickly a sound travels through the air. Advantages. Non-intrusive with no contact with the fluid. Suitable for a wide range of fluids. Applications. Applied in measuring liquid and gas flow in various industries. Used in petroleum and natural gas pipelines for accurate monitoring. Limitations. Accuracy can be affected by changes in temperature and pressure. Initial cost may be higher compared to some alternatives. Swirl flowmeters. Operating principle. Swirl flowmeters induce a swirl or rotation in the fluid stream. The resulting pressure difference is then correlated with the flow rate. Think of stirring a cup of tea and noting the resistance. The faster you stir, the more pressure you feel. Advantages. Suitable for large pipe sizes. Capable of handling dirty or viscous fluids. Applications. Widely used in the oil and gas industry for measuring flow rates. Applied in chemical processing with challenging fluid properties. Limitations. May not be as accurate as some other flowmeters. Installation requirements may be critical for optimal performance. Coriolis flowmeters. Operating principle. Coriolis flowmeters use the Coriolis effect, which is the apparent deflection of fluid flow paths caused by the Earth's rotation. The meter induces vibrations in the tube carrying the fluid, and the degree of deflection is directly proportional to the mass flow rate. It's like a dance where the fluid moves in response to the spinning of the Earth. Advantages: direct measurement of mass flow. Suitable for a wide range of fluids. Applications: widely used in the food and beverage industry for accurate mass flow measurement. Applied in chemical processing with diverse fluid properties. Limitations: higher initial cost. Susceptible to damage from particulates. Mass flow controllers. Operating principle. Mass flow controllers ensure a constant mass flow rate of gases. They achieve this by regulating the pressure and temperature of the gas, ensuring a consistent density. It's similar to maintaining a steady stream of water from a hose by adjusting the water pressure and temperature. Advantages: precise control of mass flow rate. Suitable for various gases. Applications: commonly used in semiconductor manufacturing processes. Ideal for laboratory experiments requiring precise control of gas flow. Limitations: limited to gas flow applications. Higher cost compared to some alternatives. Thermal-based flowmeters. Operating principle. Thermal-based flowmeters measure the mass flow rate by utilizing the cooling effect of a fluid on a heated element. As the fluid flows, it carries away heat, and the amount of cooling is proportional to the mass flow rate. Think of a hot spoon placed in a flowing stream of cold water. The rate at which the spoon cools down reflects the water flow. Advantages: direct measurement of mass flow rate. Suitable for gases and liquids. Applications: widely used in industries for measuring gas flow rates. Applied in liquid flow measurements where direct mass flow is crucial. Limitations: sensitive to changes in fluid properties. Requires calibration for different fluid types. Positive displacement flowmeters. Operating principle. Positive displacement flowmeters work by dividing the fluid into specific, known volumes and counting the number of these volumes to determine flow. It's akin to measuring the amount of water transferred by a series of buckets in a water wheel. Each rotation represents a known volume. Advantages: accurate measurement of low and high viscosity fluids. Suitable for a wide range of applications. Applications: commonly used in industries where precise measurement of fluid volume is essential. Ideal for measuring the flow of viscous liquids. Limitations: can be sensitive to changes in fluid properties. Potential for mechanical wear and tear. Nutating disc flowmeters. Operating principle. Nutating disc flowmeters use a wobbling or nutating disc to create a series of measured fluid pockets. The disc's movement displaces the fluid, and the number of nutations corresponds to the flow rate. It's similar to a disc dancing on the surface of a flowing stream. Advantages: simple and robust design. Suitable for measuring low to moderately viscous fluids. Applications: commonly used in residential water meters. Applied in industries for measuring the flow of various liquids. Limitations: may not be suitable for very high flow applications. Accuracy can be influenced by changes in fluid viscosity. Laser Doppler flowmeters. Operating principle. Laser Doppler flowmeters use the Doppler effect to measure the velocity of particles within a fluid. The laser beam is scattered by the fluid particles, and the frequency shift provides information about the flow rate. Think of it as observing how the pitch of a passing car changes. Advantages: non-intrusive with no direct contact with the fluid. High sensitivity to low flow rates. Applications: commonly used in medical applications for blood flow measurements. Applied in research and laboratory experiments. Limitations: sensitive to particle concentration in fluid. Doppler ultrasound flowmeters. Operating principle. Doppler ultrasound flowmeters use the Doppler shift in ultrasound waves to measure the velocity of fluid particles. By analyzing the frequency shift caused by moving particles, the flow rate can be determined. It's like listening to the change in pitch of a passing ambulance siren. Advantages: Non-intrusive with no contact with the fluid. Suitable for liquids with suspended particles. Applications. Commonly used in medical diagnostics for blood flow measurement. Applied in environmental monitoring and industrial processes. Limitations. Accuracy can be affected by fluid properties. Not ideal for low-flow applications. Thanks for watching the video. Hope you liked it. Kindly press the like button and bell icon. Do subscribe our channel. Let me know your views about the video in comment section. Do mention any topic which you want me to cover in comment section. Thank you.